Hi everybody, and welcome to another episode of Beyond GIS. I'm your host Kurt, and today we have a guest and a colleague on the show. Another Kurt, believe it or not. We talk about ourselves as K1 and K2, but actually this is Dr. Kurt Joy, and I guess we're just going to have a free-forming conversation and see where it takes us. Kurt, so how did you land here? How did you land in this world of big data and Earth observation and geospatial?
Strangely enough, it was through caving. I got really interested in how caves in the Waitomo were interlinked between themselves, where entrances were, and there was a real lack of information about where these sites were. So I kind of got really interested in getting a GPS, going to the entrances and trying to fit the old hand-drawn surveys that were made in the 1950s and 1960s and trying to fit them around these holes. And through that, I discovered sort of GIS, sort of the tools available to both kind of map where these entrances were and where these old surveys were onto sort of modern topographical maps. And so I kind of was always interested in that. And in, I don't even know what year it is, 2005, I ended up going to University of Waikato and doing a undergrad degree in earth science, sort of majoring in geology. Moved to Christchurch, and 1 year later I was enrolled in a master's program to do work in Antarctica on glacial sediments. And so, as it always does, that turns into a PhD, and then you do postdocs and you do various things. But I've always kind of have that spatial distribution of data, and accessing it and building tools that use it has always been sort of really clear in my mind, whether it was collecting hyperspectral imagery from a drone of algal mats by the side of lakes and rivers in Antarctica, or using 3D photogrammetry to build ultra high resolution mapping of human footprints to use in management plans. So I've been kind of using spatial data mostly for the last 25 years or so. So that's how I kind of ended up popping out of a cave and finding my way here 25 years later.
So I think one of the things you've talked a bit about, Antarctica is amazing, but some of that work on the dry valleys and just the amount of data and the resolution and complexity of that data. And I know, you're a technologist, a data geek like me, but what really got me when you first joined us was how to convert that into knowledge that sort of decision makers can actually understand, right? Like it's not about how many sort of decimal points you have, but actually how do you convey it to drive decision making? So could you speak to that experience a bit and that journey?
Yeah, one project we were working on was looking at how we can build management plans for the dry valleys. The dry valleys are this very old landscape. It's very complex. It's a mix between glacial sediments, lake sediments, bare exposed bedrock. So how people operate in the dry valleys has usually been dictated by 30 or 40 years worth of history of, well, we don't walk in that because it makes a mark and we can see train tracks. Not train tracks, it's actually tractor. There's tractor trails that go all the way down from one end of the valley to the other that was put there in the mid-60s, and you can still see it now. So because this landscape is so old, yet quite dynamic, because it's a lot of the sediment transport is via wind, how people operate in these valleys needed a bit of a rethink. So the project that I was involved with was with climatologists, biologists, microbiologists, hydrographers, all collecting data on various ways of how these valleys work and sort of trying to build a model around them, so that when someone goes to a certain site in the dry valley, they know how close is it to drinking water, what sediments they shouldn't be walking on, how they should set up their camps, what things they should be looking for. And so you've got all the scientists building stupidly high resolution data sets. We had one person who was doing stuff with a ultra high speed thermal infrared camera at 300 frames a second. So there's that kind of data coming out, and he was looking at the boundary layer and looking at how air movement happens over these kind of heating lakes. But at the end of the day, the project wasn't about building all that data, it was about answering questions. If someone wants to go to a camp at one place, what's the outcome? What do they need to know? And this goes all the way up to government level, to central government, when they're looking at this area. It's what they call an Antarctic Specialty Managed Area, an ASMA, which means you have to have permits to go in this area, and there's even areas where you need another set of permits to go in. So it actually gets signed off by one of the ministers. So they need to look at it and go, if this person wants to put a campsite there, is it a yes or is it a no? But the person beneath them, another layer of that kind of bureaucracy, wants to go through and say, well, what are the reasons for that? And sort of delve down. So I've always been quite aware of this top-down view of data and having the ability to kind of thin slice out what you need to know to who needs to know. And so that was coming from the other side. That was coming from, scientists collecting petabytes of data to someone who wants to click on a map and see a red or a green dot. So I've got it's been a really interesting experience coming from sort of the big data to actually stripping it down and trying to find information from that big data.
When you've been, if you look at your journey in the last few years at Orbica, we were working for multiple customers, trying to make sense of data and drive decisions inside their business. How do you sort of reflect on that world of sort of research and academia, but then in the world we play in, which is how do we help sort of more apply the research of the science to the actual BAU processes inside an organization day to day?
Yeah, and you're completely right. It's that abstraction of information from data. You need the academic rigor, the publishing that goes along with it. So when you make a decision that's going to affect multiple people, whether it's financially or sustainability, they need to be able to make a decision using your tools that are based on the best possible data. So you need to be assured that what you're providing through an equation or some sort of environmental measurement is actually telling you the right things at the right time. And I think that is the big switch in the last few years, is going from these big data sets where people were going through them and trying to extract value from them, and now having more tools like machine learning, artificial intelligence algorithms that allow us to sort of start extracting out some real information out of these complex and large data sets.
I think you touched on, in a couple of the prior episodes, we've looked at sort of trust in the eye of the decision maker. Yeah. So lots of complexity, lots of math, lots of novel work sometimes, in terms of algorithms and how to expose and find value. That transparency, I think you sort of touched on it then. Like, what does that look like from a sort of data practitioner or scientist perspective to sort of open the kimono in a sense and show people in a white box transparent way everything they've done? Input data, processes, assumptions, pros and cons, limitations. So a decision maker's got that knowledge when they're making a decision. Yeah,
and I guess it's that data assurance and that data quality. And what we see now is a lot of data sets that may have come down from a satellite, whether it's imagery, whether it's some sort of other sort of active data that's come down, and go through a series of processing steps, when what we're seeing more now is larger organisations are taking that on themselves. So they will take the data, they will clean it, they will prepare it and release it as something called analysis-ready data. And that's kind of the gold standard benchmark of that data being used for further analyses. You're making sure it's all calibrated, it's all sitting in its right place in the world, it's had orbital corrections and 1,000 other sort of micro corrections on it. But what it allows you is that assurance that when you access that data and do something with it, you know that you're starting with a good product. So there's been a big move to these analysis-ready data products, especially in the sort of the Earth observation satellite world.
I mean, if we touch on, actually, let's go back a step. So you've touched on GIS, you've noted sort of Earth observation, geospatial. What's your sort of view of GIS and kind of where it's been, what geospatial is, but then we talk about here this concept of sort of digital geography, which is the next layer in a sense of driving understanding and knowledge.
Yeah, I guess I guess I've never really described myself as a GIS person, or I suppose I'm kind of a spatial analyst, but it's about data filling the need to answer questions and not the other way around. Quite often we see data sets come out and people will go, I'm going to look through this data set and I'm going to answer a question. Where in all of these kind of domains we're seeing now, they're coming up with questions and saying, we need to find gravel extraction on the side of one of the Canterbury rated rivers. How do we do that? What do we need? What technologies even do we need to be able to do that? Mm-hmm. So you're also sort of driving algorithms, processes, even the data itself to answer a question. So not pulling data out and for data's sake answering something. And a lot of good things have come from that, but it seems to be more driven from the end users now rather than doing the analytics on the data.
Do you think it stems a little bit if we look at space and what's happening in space again, the rejuvenation, I guess, of the space sector, launch costs, SpaceX, Rocket Lab, yep. Enabling access to space, which has lowered the cost of access to space. But now we're in a world, I think, of instead of putting up bus-sized satellites, to put up, CubeSats.
Yep.
And that ability for a university to potentially design and launch a CubeSat, but completely focused on collecting data for the problem identified first.
Yep.
How are you seeing that happen and sort of the volumes of data that they're producing?
Again, the kind of the CubeSats have really put a big spin on things where you can have, for relatively cheap, still talking sort of $50,000 to get into space, Kiwi, but you have the ability to put science experiments into space. So again, it allows little questions to be asked relatively easy. How do crystals form under 0G? How do microbiology react when you're in 0G? And that whole, as you say, the rejuvenation of the space industry going from these large bus-sized Landsat and Sentinel satellites, the NASA, USGS and European Space Agency kind of platforms. You're starting to move into smaller platforms, and that also a move from one single satellite, and as we've seen with Maxar, when one thing breaks in your satellite and you can't save it, it's not being fixed in a hurry, to sending up multiple of a satellite, which forms a far more niche role, particular instrument that may only look in a certain visual part of the spectrum, electromagnetic spectrum, but it allows you redundancy. And what is more important for this kind of big move about Earth observation is it allows that multi-temporality. We're getting the revisits between collected information far higher, at a far higher cadence than what we see with the big satellites. We used to think Landsat was really good with, a 16-day, 2-week kind of revisit to site. Then we had, the Sentinels with a 5-day revisit over a site. And now we're getting small constellations doing multiple sites multiple times a day. So it's really kind of opened the market to how people consume and how people get value out of these data sets, especially in that kind of land use monitoring and environmental monitoring sort of domains.
Yeah, it's interesting. I mean, the high we talk quite a bit about, I guess it's because it's imagery, it's visual, you can interpret it, that it's really easy to pick holes in, maybe that extraction algorithm to pull out those buildings isn't 100%, the vertices slightly off.
Yeah.
But actually we're starting to now drive a narrative. Does the absoluteness of the accuracy of your polygon you're pulling out of the imagery matter, or is it actually the change over time that matters?
Yeah.
Right? And so the trend. And so I think that is really interesting to think about actually the trend is way more important to me driving decision-making processes in the business than having a one-off snapshot once a year of a perfect building outline.
Yeah.
So how do you sort of frame all that in your...
Yeah, I mean, that's... The accuracy of these satellites are pretty good, considering it's basically a camera in space that's taking a photo through the atmosphere that gets fitted into its correct geospatial coordinates on Earth. That sort of auto-rectification if you need to move it, and the georeferencing of these images is almost secondary to the the data that's coming out at a temporal scale, and especially with instruments that either do multiple bands or have multiple instruments on a satellite. So whether that pixel is out by 1 meter or 2 meters doesn't really matter, but it's the fact that we can go back to, in the case of Landsat, back to the mid-70s and have a look at what's changing over that area is far more important, especially when you're looking at it sort of in the context of not just what we see with the naked eye and sort of red, blue, green space, but also outside of those and in the near infrareds and the short waves and the thermals, where we can start looking at skin temperature on the Earth's surface temperature. We can start looking at water absorbance in plants. We can look at plants' health. So all of these are sort of really interesting things that the spatial resolution on the ground isn't really important. Landsat's 30 meters a pixel, Sentinel's 10 centimeters a pixel. They're still quite coarse compared to a lot of the sort of the high resolution satellites that are coming out, which can go down to 50 to 30 centimeters on the ground. But it's the long time period, the long series of records that are being captured by these platforms that are the real interesting sort of where the most interest lies. How has things changed over time is more important than where exactly has that change been? So in the world we live in, particularly in big government, big corporate, big entities, a lot of the analytics and consequential sort of reporting and dashboarding and stuff, it's all after the fact. Yep.
So with what you've just talked about and that sort of temporal view, how do you sort of see advanced data analytics, AI, geospatial analytics, all sort of converging to understand the past, but actually more importantly to help predict proactively the future, rather than going, hey, we did this awesome, water quality monitoring. If we knew that 6 months ago, when it was near real time, we would have made XYZ decision.
Yep.
But hey, we got the report 6 months later telling us what we should have done, but that's, again, useless. How do you see all that sort of converging?
And it's interesting that, the two sort of long-term open access, so these are data sets that anyone can jump online and get them, which are the Landsat program and the Sentinel programs, they're both kind of been driven by that. Sentinel was, the Sentinel satellites were not put up to collect data, they were put up to support a program. And so we look at the Copernicus program, and one of theirs is we need something to do ocean observation, we need something to do land class observation. Well, what do you need to do answer that? Well, we need a couple of satellites. Cool, we'll build satellites that do that. And in the case of Landsat, it's newer and better technology has come along, but they've decided that using a platform that has a continuous record back to 1970 and all this, even though they're different satellites, they're all designed to sort of fit within that same parameter, really kind of allows questions to be asked that probably wouldn't have been able to do it if you had approached it any other way. And so now we've got from 2015 to present for Sentinel-2 every 5 days. Now, it's a big data set, it's 10 bands, it's quite a high resolution spectrally. What things can you put on top that can be trained on past change to predict things in the future? Can we build models that are sort of looking at these long-term trends that we see in these records? And 2015 to now is only 7 years. It's not really a long-term trend, but because of the temporality of it, it's still a data set that's good enough to sort of be able to sort of separate out trends from more seasonal effects on land cover especially, and ocean temperatures.
Something we've been exploring lately, so you've talked a bit about, lots about imagery, multiband, a little bit, you touched on hyperspectral. Something we've been exploring with and dabbling with is SAR, synthetic aperture radar from space. What's your view on it? Very quickly it relates here in New Zealand where, it's the land of the long white cloud.
Yeah.
It's difficult, particularly in the mountains, particularly on the West Coast, sometimes across a whole year to actually get cloud-free pixels of our country.
Yep, like everyone sees these wonderful pictures of New Zealand done by satellite, but it's actually the it's either a statistical product of multiple years worth of data, or or even a single year of data. And even I did one for New Zealand, so it's a full cloud-free mosaic of New Zealand. So it's using data from Sentinel every 5 days over an entire year, and there were still pixels that were empty, that have always had cloud on them. So it's really hard in a country like ours, and it's kind of the bane of not just satellite imaging, but also aerial imaging, LiDAR. You've still got to be able to fly in these conditions. And water in the atmosphere basically obscures lots of stuff. You can't see through clouds unless you use a technique like SAR, synthetic aperture radar, which uses an active sensor. Basically, it's kind of the sci-fi version of the ping from a sonar in a submarine. It fires out a microwave signal which gets scattered on the surface and then collected back at the satellite. And because it's microwave, it's not either in the visual or near infrared spectrum. It can fire through and basically start resolving a variety of ground properties and surface properties through fully obscured clouds at night, whenever it can do it. It's very commonly used in the marine security industry worldwide for picking up ships, especially ones where transponders have been switched off and they suddenly deviate from where they're supposed to be. These are these ghost ships. So SAR can be used to track those because you've got a nice flat ocean and a big shiny reflective thing floating around. In New Zealand, I think it's going to be used more and more, especially we've done a few trials with looking at monitoring wildfires using SAR. Again, wildfires in New Zealand, it's cloudy, it's got smoke cover. SAR can see through all of that. We can start seeing the disruptive nature of the fire on the surface it's sort of consuming. So while it's an old technology, radar, sat, and there's been a whole bunch of satellites have been around for a long time, I think its use is now becoming more and more prevalent in a whole bunch of different industries and domains. And that just shows with the amount of new players in the space operations scene who are launching their own satellites and SAR, when they're not just buying and selling SAR data, they're putting up their own constellations of instruments to collect data constantly. And I think the highest resolution on the ground is about 50 centimeters at the moment, so day or night, 50 centimeter imagery. So it's a big field that's going to become more and more useful in not just kind of land cover stuff, but also altimetry and building up high resolution 3D models of vertical change.
What's your view on why it hasn't been utilised too much yet? What are those sort of trends going on that it's between knowledge and compute and actual data availability in the cloud? How are you seeing that sort of bundle together?
In SAR, it's a complicated data product. It's if we think about multispectral stuff, you can kind of wrap your head around it going, well, it takes a photo on 5 different things and it basically 5 different images. With SAR, it's because it's looking at the reflection and the backscattering of a radio signal or microwave signal. The data is not so much an image, and even when you get an image back, it's not something that you can interpret straight off the bat, because there's different ways of viewing the data, there's different ways of processing the data, and it is quite time consuming. And while there are some companies out there that are taking free SAR data, such as what comes from what they call the Sentinel-1 satellites, it still needs processing. It still needs a better eye on how to interpret it. It's a bit more complicated on the interpretation of it compared to you look at an image and you go, oh, that area is blue. It's probably a lake. Where you can't do that with SAR because of a bunch of different sort of factors that generate the image that comes out.
Is it, I guess, it just has to go on the maturity cycle, I suppose, to start to create some analysis-ready data products and for more people to focus on that. So
exactly.
I don't know, a data scientist can pick it up and actually use it in his workflow.
Yeah, and there are some companies that are doing sort of relatively prepackaged data products, analysis-ready data products in a couple of formats to look at certain things, look at water, roughness of the surface it's bouncing off. So there's a few things that are already out there that can be used and applied in different things. But like all these technologies, until people sort of start sitting there and start applying it and using it, sometimes you don't find the uses until you just basically start playing with the data.
I mean, at the end of the day, right, it has to go down the value chain so it can be understood by a decision maker, someone funding or in charge of an outcome in a business, and that, you know, geospatial as a whole needs to go on that journey. It's still very, you know, particularly the world of GIS, it's unknown. So I don't know, in your experience, you know, what's that journey look like again of that sort of siloed GIS world, kind of where we've come from in a way, but then to the broader world of geospatial and democratization, like what Google Maps started in the consumer world, to sort of where we are now about driving those outcomes into business and making it understandable about why space, place, geospatial, location, geography matters at a business level.
Yeah, I mean, it's a really interesting time because, and I say Google's to blame for all of this because Google gave GIS to the masses. It made everyone in their phone, on their computer, use at some level GIS data. They're interacting with the data, whether it's traffic flow, whether it's points of interest, whether it's the satellite imagery they look at in the background. The world has got a lot of expectations because of what Google has done with that, you know, and we've had clients who go, yeah, but look at this. Why are you telling me you can only get me 10 meter resolution imagery? I can see my dog in this. And then you say, well, your dog died 2 years ago. You know, this imagery isn't up to date. So while it is high resolution, it's the temporality, the constant collecting of change, which is becoming more important, and that's really driving business questions. And because of those business questions, it's feeding back into what do we need to answer these questions? What data is already out there? What data can we fuse together with other pre-existing data through that data fusion kind of process? And how do you use the petabytes and zettabytes and huge amounts of data that are out there? How do you start using that to answer questions that people haven't thought of before? People have probably thought of the questions. It's basically going, what do you need to answer those questions? What data sets are available? What techniques are available?
Yeah, it's interesting, right? It's so, you need the culmination of so many factors coming together, I think, for a successful delivery of an outcome. So you might have the lead asking the question.
Yeah.
But then what's that translation? So much is lost in translation of that through the deep technical people and between the business needs and the technical people. And then often beyond that, again, a siloed GIS team.
Yeah.
How do we start to bring geospatial tools data to the fore?
If you're working in a hydrology project, you need to know a little bit of hydrology. You know, you need to be able to talk the talk. So when the client comes and says, I'm trying to do this, I'm trying to map river flow. And you go, oh, okay, yeah, that's a stage value. We can see it going up and down. Cool, time series, that's easy. But when you don't have that link, it starts getting far more complicated, that things can get a lot fuzzier. And so the only way that can happen is through the collaboration between, you know, the end user, the subject matter expert, the people who are doing the analysis, and the data itself.
You touched on it there, and you talked about sort of stage sensors and sort of river flow networks. And I know you're doing some work in that space, but we talked a bit before about sort of space for Earth, in a sense. You know, I'm really interested to Internet of Things and connected sensors. You know, what's your view on that? So there's also an in-connection to the enablement in space. If you think Starlink, for instance, you know, broadband every place of the planet coming our way. What does that mean for the ability to collect real-time information of the environment, human interaction of it, to drive, again, decision-making processes?
Oh, I mean, it's key. You know, the more data you can collect at the surface not only makes the data that you collect from space better because you can calibrate it, but it also allows you to sort of start deploying things a lot cheaply. You don't need to buy data. You might be able to use cheaper data or free data off these satellites if you can calibrate them to the surface, you know. And a couple of years of working down at Antarctica, we would actually go out and we would be putting out these giant calibration tarps, basically 4 different colors, kind of 4 or 5 meters across, spread them out. And that's for when Worldview was coming over and had been tasked to take imagery over us. They would be taking it at the exact time of day where someone would be going out with a handheld spectrometer and basically measuring the wavelengths of what's being done so they can calibrate the satellite. And so if you think about that concept with data products that are coming out of these for water quality, all these kind of things, you know, by getting a combination of the real sort of measurement to the sort of the imagery that's collected, they can be calibrated together. That's where you start getting far more accurate orbital collected data for the questions that you're trying to answer.
I mean, do you see a world potentially, certain use cases, you could have sort of automated calibration algorithms almost in a sense, real-time sensor networks, talking and working with the satellites, some AI model of some description in between, constantly adjusting and reinforcing and relearning based on, you know, new conditions down on surface. Which I think, I mean, what I'm really interested in is that fusion aspect of how do we extend the value of the pixels in space, so to speak. Hey, certain networks in the right position to ground truth then allows us for proper interpolation in a much broader area.
Yeah, and that also brings into that whole computation on edge as well, which is doing, you know, doing the hard computation work, the data intensive stuff, doing it on platform in space. So then you're getting the derived outputs from that push to Earth at a quicker cadence.
So instead of, I don't know, you're not pushing down cloud pixels, we're dumping them out of the satellite and pushing down the data that's useful.
Yeah, instead of collecting, you know, like, especially, this is really important when you start going in from that multispectral where you might have 10 to 12 bands, going to hyperspectral, which is anywhere from 200 to 1,000 bands. If you're already doing some process up there, building a product and then passing it down to the ground stations, you know, it's a lot less data to push.
So I mean, that concept of analysis ready data, we should be able to automate as much of that as possible. So it's actually analysis ready the moment it's beamed to Earth in this case.
Yeah, exactly. And you know, all of these kind of instruments, especially the optical instruments, need calibration. Because as we know, you know, when it starts getting to dawn and when it starts getting to dusk, the color of the sun changes, therefore the colors you see on the landscape are a different color. So it's those kind of things that need to be sort of calibrated out if you're trying to actually start mapping things based on their spectral responses.
I mean, there's an angle to that too if we think about terrestrial data collected down here on Earth, and that sort of, we're looking at ESG stuff, right? Power, solar, carbon-free, thinking about big data centers. You know, we've talked quite a bit about in previous episodes, so much data is just not utilized. It's just sitting there on hard drives in storage, and we're touching 1% of it, 5% of it, the potential of it. So this way, I think, to find the value in the data and actually just get rid of the stuff we're not using because there's no utility in it.
No.
I guess you could, that comes down to IoT sensors on the edge as well, down here. Why send data that's useless? Derive the results on sensor, store and manage that, and drive your big data center type processes.
Yeah, exactly. You know, if and because of the sort of the new generation of embedded devices and phones that have got sort of GPU acceleration on them, or libraries that we can start doing AI on it, you kind of step into that world of, you know, machine learning on edge, where you can start doing a lot more of those smarter processes on the device before that data gets pushed somewhere, whether it's, you know, through up to Starlink and then back somewhere else, or whether it's via a cellular network or a radio network. There's a lot of those kind of things that can be done. There's a lot of things that can be done at the hardware level that allows the data to be quicker to access, especially when it comes to real-time stuff.
Before we wrap up, what do you think? What's one thing you're excited about in terms of you kind of could really move the needle on, propagating the value of geospatial into places it's not already, and sort of driving forth this concept of sort of digital or modern geography in today's world?
I guess it's just the ability for people to do things a lot easier now. My first year down in Antarctica, I had Lima cloud-free mosaic stuff off Landsat, and I thought, oh, this is great. Look, I can see my glacier. This is cool. And one of the guys there goes, oh, I've just got some stuff from the Japanese space program, and showed me this 3-meter imagery, and it was like, what? Where did this come from? And we now know that this stuff is out there. It's easier to get. The amount of data that's being developed and downloaded and also developed into sort of derivative products is so much. There's so much data out there, and I think just the ability of anyone to kind of jump on Google Cloud, AWS, and start doing their own analytics is pretty amazing. It's a pretty amazing time to see, what is available for people to do their own science and look at stuff from space for free.
Hey, look, thanks for your time today. Enjoyed our chat, and I'll see you around the office.
Cool. Thank you very much.